All right, for those of you who have been with us before, welcome back. And if you're looking at this one for the first time, welcome. What we're going to be looking at in this topic is we're going to continue with the relationship between magnetic fields and electricity, or electric fields. And what we're going to look at in particular in this section is the motor principle. And that's going to bring us to the third left-hand rule. And we're also going to look at some of the equations that we use to analyze magnetic fields and magnetic forces and things like that. So we'll start out with something called the motor principle. And we're going to do this topic in two halves. Okay, this first half that we're doing here now is just going to be the theory part of it. We're going to run through all the instruction behind the topic. And then in the second half of the recording, we're going to take a look at some questions off of OLPublics. So that's going to be a separate recording altogether, in case you're wondering. So if that's what you'd rather see, then you look at part 2. Anyhow, we've already talked about the fact that a current-carrying conductor has a magnetic field around it. That was Ørsted's discovery. What we're going to take a look at now is what happens if that current-carrying conductor, with its magnetic field caused by the current, what happens if that's placed within the field of a permanent magnet? Well, remember that magnetic fields interact with each other. Like fields will strengthen and repel, and opposite fields, or opposite directions, will weaken, cancel each other out, and weaken the field. So one magnet can actually make the other move. If you take like two north poles of magnets and try to push them together, you can actually feel the force between them. And that essentially is the principle by which an electric motor operates. Okay, two magnetic fields will either attract or repel each other depending on their direction, and that makes the inside part, the spinning part of the motor, move. We call that the rotor. Anyway, that's the motor principle. Two magnetic fields interacting can cause the other one to move. Now, there are there are two magnetic fields needed to cause an electric motor to operate. There's first of all a permanent magnetic field, which is normally in the form of permanent magnets in the outside casing of the motor. And there's a temporary field that we create when we pass a current through a coil inside the motor, in the part that spins. Okay, and that way we can turn the motor off by turning off the current, and it won't spin anymore. Okay, so that's an electric motor. Permanent field with permanent magnets, but there's also a temporary field that we create when we pass a current through the coil that's inside the motor. So here's what it looks like, essentially. Okay, we'll start with this. What would happen if we just took a wire? Let's forget the coil for a minute. Let's just take a wire. We're going to suspend it in a magnetic field like you see here in the picture. Okay, and what we're going to do is we're going to turn on a power source. So electrons leave the negative terminal of the battery. They follow these blue arrows here, which means they come down this side, through this piece of wire, this conductor, and then back up again. Okay, all the way back to the positive terminal of the battery. Now, if you then took this current and use your left-hand rule number 1, the one for straight conductors, where your thumb points in the direction of the current, and your fingers wrap around in the direction of the magnetic field, you will get these pink circles here, which means that over here on the right-hand side of that conductor, the field is going down, whereas on the left-hand side of the conductor, the inside here, the fields are going up. That's the field caused by the flowing current. But there's a second field with the magnet. And remember, the magnetic field around magnets goes from north to south. So the magnetic field line, the permanent magnetic field between the magnets, the black lines, are all pointing upwards. That means that on this side over here, the outside we'll call it, the magnetic field lines of the magnets are pointing up, but the pink lines representing the magnetic field around the wire are pointing down. So because they're opposite like that, they cancel and the field gets weaker on that side. On the other side, both fields are pointing up. The pink one caused by the current flowing through the conductor, and the black lines, which is the permanent magnetic field, they're in the same direction, which strengthens. So what happens is the conductor gets pushed this way, out of the magnetic field. That is essentially what happens inside an electric motor. That's what happens inside an electric motor. Okay, the force that is created between the permanent magnetic field and the magnetic field caused by the current flowing through the coil of wire inside the motor, that's what makes the motor turn, that force. We call that the motor principle. Now obviously that's not much of a motor, is it? So we're going to look at what a motor actually looks like in a second, but before we do, there's an easy way, without having to draw all these magnetic fields, there's a really easy way to tell the direction of that force. And that way is left-hand rule number 3, our third left-hand rule. And that's the last left-hand rule. There's only 3 of them. Left-hand rule number 1 for a straight conductor, thumb in the direction of the current, fingers coil around in the direction of the magnetic field. Then we had left-hand rule number 2 for coils, which said that your fingers wrap around in the direction of the current through the coil, and your thumb points in the direction of the magnetic field leaving the coil at the end, or the North Pole. Now there's a left-hand rule number 3, which is for motor principle. When we have a conductor in a magnetic field, typically a straight conductor, and it's carrying a current, and T got cut off there by the picture, sorry about that. It's carrying a current. We can find the direction of the force by using left-hand rule number 3. Left-hand rule number 3. Okay, so a straight conductor in a magnetic field carrying a current experiences a force because of the interaction between those two magnetic fields. Now what we're going to do is we're going to look at how you can tell what direction the force will be exerted just by using your left hand. And here's the way it works. You take your left hand and you orient it so that your fingertips, right, you just hold your hand straight this time. You don't coil the fingers. Just point your fingers nice and straight with your thumb out in the shape of an L. Left hand. Fingers point in the direction of the permanent magnetic field. In other words, from north to south. That's the direction your fingers point. Your thumb points in the direction of the current in the wire. When you do that, your palm will point in the direction of the force. Picture an arrow pointing out of your palm. That's the force. Okay, and they're all done in different colors here. You notice the magnetic field black, that's this one. Then the current direction blue, that's this one. And the force green, right there. All color-coded. And you'll also notice that everything is perpendicular. Right? Your fingers are pointing straight up, your thumb is pointing straight out, and then your palm is pointing straight to the right in this example. And if we did that with this guy back here, okay, if we pointed our fingers straight up, because that's the direction of this permanent magnetic field, our thumb pointing straight out, because that's the way the current is flowing out of the page, your palm would point to the right, which is indeed the direction of that force, and we wouldn't need to draw any of these magnetic field lines to figure that out. Just use left-hand rule number 3. That's the easiest way to do it. And we're going to apply that in a couple of cases now in just a little bit. Now, so that interaction between the two magnetic fields can kick the conductor out of the magnetic field, but that's not much of a motor. That would just move it out. Then that's it. Everything stops. Nothing happens. So the magnetic fields can produce motion, but how do we make it produce a continuous motion? Well, to make a motor, we have to have a piece in the middle that rotates. So we bend it into a loop like this. And we set it up so that each side of the loop is connected to a different strip. See this? We call that a split ring commutator. And we're going to talk about that term again in our next day of classes when we talk about generators, because that's also found in a generator. But right now, the only type of motor we look at is a DC motor, so a DC power source. In other words, the power is direct current. It's flowing in the same direction all the time. That's it. So leaves the negative terminal of the battery, flows in here. This one here labeled G, that's a brush. That allows contact between this and this, so the current can flow through. So the current flows into side E right here, up through the loop, back around, and down this way. These magnetic fields here interact with a permanent magnetic field created by two magnets, one on either side, and the magnetic fields will be stronger or weaker on the bottom and the opposite on the top. And when we get to the other side, because the fields are going in the opposite direction, the direction of the force would also be reversed. For example, if we had our permanent magnetic field going this way, let's say that was our permanent field. Okay, you point your fingers that way. Your thumb would point in the direction of the current, and for this one right here, your palm would point straight up. So the force would be that way on that side. But on the other side, your finger's still pointing to the right, but this time your thumb pointing out of the page because the current is in the opposite direction. Now your palm points down. So the force would be down that way. So one side gets pushed up, the other side gets pushed down. That causes a rotation, just like a seesaw. Remember when we did the torque section? Just like what happens in a seesaw. Whenever you have one force pushing up and another one pushing down, that object rotates. And as soon as it rotates half a turn, then E and F, right here, they trade places. In other words, E is now on this side, F is now on this side, and the whole thing repeats over again. Because if it wasn't for this split ring, what would happen is it would get over here, okay, and then this one would be pushing down because the current would be still flowing in the same direction it was, and this one would go up. So it would just tip back and forth, back and forth, back and forth. It wouldn't spin around. So that wouldn't be much good. That doesn't really accomplish anything. So that's what the purpose of the split ring is right here. To keep it rotating, to swap the sides, and to keep the current flowing around the loop. So it's always flowing into the page on this side and out on that side. So that's a motor. Now, there's not usually much in the way of questions on the motor itself on your public exam. What usually is there, though, is calculations involving the strength of the magnetic field. And it's pretty easy to figure it out. There are a number of formulas we can use for that. In fact, there's 3 formulas on your formula sheet that deal with magnetic field strength. Okay, so if we want to determine the size of the force acting on our conductor, in other words, in the motor principle, there's a formula for that. Okay, there are several things you can do to change the amount of force. Okay, first of all, we could increase the size of the permanent magnets. We could put stronger magnets here. And by doing that, that would increase the permanent magnetic field, which would give us more force. Okay, more force. And by the way, the symbol for magnetic field strength, you should remember, is the letter B. B, and it's measured in T, or Tesla. Anyway, we could also make the circular magnetic field in the current carrying conductor stronger as well by putting more current through. So in other words, the force on the conductor is proportional to the current. So it's proportional to the field strength of the magnets. It's also proportional to the current. It's also proportional to the length of the conductor, because the longer the conductor, the more interaction there is there. The more room there is for forces to be exerted on the electrons in that wire. And it turns out that's direct proportions as well. So F, force, is also directly proportional to the length. Okay, so there's 3 things that affect the size of the force: the magnetic field, the current in the conductor, the length of the conductor. And there's one more thing. It turns out that the angle makes a difference as well. We get our maximum force when the electrons are flowing through the conductor perpendicular to the magnetic field. If it's perpendicular, that's the maximum. When we turn it at an angle, the force gets smaller. Force gets smaller as you change that angle. the smaller the angle gets between this and this, in other words, the closer it gets to 0, the smaller the force gets. The smaller the force gets. In fact, if we turn it all the way to 0 degrees so that the conductor is actually parallel to the field, the angle is 0, we get no force at all. The force actually disappears. It actually disappears. So the conclusion that we can make for that is the angle is important, obviously, but it's not the angle itself, it's actually the sign of the angle that's most important. It's the sign of the angle. The sign of the angle is actually directly proportional to the force. Directly proportional to the force. So we put it all together and we get this relationship right here. F, or force, is proportional to field strength times current times the length of the conductor times the sine of theta. And as with any proportion, we can put a proportionality constant in there to make it equal. Now it turns out that that proportionality constant, we could have called it anything, but what was decided when they were working out these relationships is they said it'd be a whole lot easier, you know, because we don't have a unit for field strength yet, let's create the unit so that our constant will be 1. K becomes 1. If we define our field strength in terms of these other units, the force, the current, and the length, then our constant can be 1. So in other words, the unit that we use for magnetic field strength is defined as 1 Tesla of field strength is defined as the amount of magnetic field strength that would cause a conductor that's 1 meter long to experience a force of 1 Newton when the conductor is carrying a current of 1 amp and it's perpendicular to the magnetic field. So that is the definition of that constant. So in other words, if K is 1, we can just say this. F equals BIL sine theta. Sometimes we call that Bill sine theta. That formula right there is on your formula sheet. It's given. You just got to remember what each of those terms in the equation equals. So here it is. B is the field strength. I is the current. L is the length. Theta is the angle, but it's the angle between the magnetic field lines of the permanent magnet and the line of the conductor. In other words, the direction that the electrons are flowing. The angle between that. Perpendicular is your maximum force. Okay, so if that's our field strength, then it'd be nice if we had a way to measure it. Well, Oersted discovered that there is a magnetic field around the current-carrying conductor, and its direction is determined by left-hand rule number 1. But what about its magnitude? Well, it turns out that the larger the current that flows through the wire, and we just said this a minute ago, the stronger the magnetic field is. But it's also true that the larger the distance is away from the wire, the smaller the field gets. Right? It gets weaker as we move away, which also makes sense because most fields act the same way. As we get further away from the source, the field strength does decrease. So putting all that together, we know that B is proportional to I over R. So again, to make it equal, we put a constant in, and our constant has to do with the magnetic permeability of the substance that is surrounding the conductor. Normally that's air. So if the field is in free space, like a vacuum, or it's in air, because air is so close, we say it's the same thing, here is the magnetic permeability. That number is also given on your formula sheet, so you don't need to memorize it. And that relationship then, we get rid of the constant by saying our constant is actually this over 2 pi. There's our constant. Mu over 2 pi. Mu is the magnetic permeability. Okay, so B is the magnetic field strength in Tesla. Mu is the magnetic permeability of the substance. I is the current. R is the perpendicular distance away from the conductor. We drew a line perpendicular. We drew a normal line out from the conductor. That would be the distance, the length of that line. And remember that most of the calculations you're going to do, in fact, I would say all of the calculations you're going to do with that expression, which is known as Biot's law, all of those use this magnetic permeability, because we're pretty well exclusively dealing with in air. Or the insulation around a piece of wire, same thing. They're all pretty much the same. Unless you put a piece of metal there, close to it, then that number is not going to be any different. So it's 4 pi times 10 to the negative 7. So that's 2 formulas. There's one left. One more formula. We got the magnetic force on a single moving charge. We already talked about the magnetic force on a conductor carrying electrons. Well, that's F equals BIL sine theta. And the key is current carrying. In other words, carrying a current. Well, remember that a current is moving electrons. So really, there's moving electrons inside that wire. That's what the force is exerted on. The force is not really exerted on the wire itself, because as soon as the current stops, there's no force. So it's the current that's important. And the important thing to remember is the current is electrons. If we took the conductor away altogether and shot a stream of electrons instead, we'd still get the force. The force would still exist. Only this time, L would be the length of the stream of electrons. That's it. The length of that stream of electrons. So we can devise another equation for that, which is what we're going to do here in just a second. But the other important thing to remember is when we're talking about single charges, it doesn't have to be an electron. It could be a proton. It could be a neutron. It could be an ion. It could be lots of things. That anything that has a charge will be affected by that magnetic field. So we're going to call the charge Q. And that charge Q, traveling at a speed v, takes a time of t to travel a distance L. Now, that's a mouthful. But there is a relationship between L, v, and t. It's d equals v times t, right? Distance equals speed times time. You should know that. That's your basic uniform motion equation. So because the charges are moving, they follow that relationship. So I can say L equals v times t. That's d equals vt. And because there are n charges, because usually it's a stream of charges, if we think about a stream of charges, the total charge would be n times q. And I equals charge divided by time, q over t. So because there's more than one charge, I can say nq over time. Now, what we can do now is we can put all that together and substitute it back into our first equation to get a new equation that deals with just one charge. So here we go. Use I equals nq over t. Now, you don't need to remember all this. It's always nice to know where the formulas come from. I find it's always nice to know that, because if you ever forget the formula, sometimes you can remember where it comes from. Anyway, I equals nq over t. L equals v times t. We substitute those in for I and L. So we get bnq over t times vt. The t's cancel, leaving me with this. F equals bnqv sine theta. So that's n charges. But we're looking for a single charge, so I'm going to say let's let n equal 1. And if n equals 1, we get this. bqv sine theta. But it's written like this on your formula sheet. qvb sine theta. Just changing the order, that's all. Where q is the charge, the magnitude of the charge in coulombs. V is the velocity of the charge in meters per second. B is the magnetic field strength in Tesla. And theta is the angle between the velocity vector of the moving charge and the magnetic field lines. So in other words, if it's perpendicular, we get our maximum force. If it's parallel, we get no force. Simple as that. No force if it's parallel. All right, so those then are the 3 formulas. We had F equals BIL sine theta. That's on the formula sheet. We had B, the magnetic field strength, equals mu I over 2 pi r. That's on the formula sheet. The value of mu is on the formula sheet as a constant. And then finally, we've got F equals QVB sine theta. That's for a single moving charge. The other one is for a current in a wire. This is the one that's kind of the odd man out. So that brings us to the end of the theory on this stuff, where these equations come from. What we're going to look at now in the next recording, in other words, part 2 of topic 14, is we're going to take a look at how those things apply to questions from old public exams. Okay, so if you're planning on continuing on, that will be a separate recording. So good luck, everyone. Study hard, and come back and join us again.